for giving me the opportunity to talk about our work. Okay, so let's move on. Okay, so you see my slides fine?
Yes.
Good. So enormous amount of textual data is available online in many different forms. For example, we have text in like paragraphs. We have a collection of articles, for example, news articles, or even a really large scale textual data in Wikipedia. All of these are unstructured text, but we might have textual data also available in a structured form, like Wikidata or scientific knowledge bases, or even some textual data in different formats, like in multimodal formats with different kind of visual data accompanying them. Or in different domains, like most of the text that we usually care about is about news article or, for example, Wikipedia type articles. But what happens about domains like scientific articles? Okay, how can we tame this information overload where most of these information are in textual form? This problem of textual comprehension and reasoning is basically one of really important problems across natural language processing and AI. And I could think of three important components in this type of problems, which is retrieval. How can we pinpoint and retrieve necessary information or like important information that we are looking for? Comprehension. How can we go in and dive in and understand the meaning of text within each of these kind of paragraphs or documents? And then reasoning. How can we connect different pieces of information together, make multi-hop connections, and be able to reason and understand really what is going on inside those articles? And usually this is a kind of a loop, like for example, retrieval would lead to comprehension, would lead to reasoning, and so on. Okay. Usually people evaluate the capability of textual comprehension and reasoning through some extrinsic applications. For example, question answering. What do I mean by that? Let's say we want to build a system that is able to answer a question like this. What percentage of the Washington state budget has been spent on education over the last 20 years? If you ask this question from Google, it will basically gives you a list of articles that are related to this question, right? It's been retrieved, but it's usually a user's job to go and connect different pieces of information from these resources to finally find the answer to this question. But what we really like to be able to do is to first understand and comprehend this question, to understand that we actually want to compute this answer to this equation, and then find the information across different forms like tables or kind of news articles or financial records and things like that, aggregate all these information, and then finally answer that question. Or another application domain such as fact-checking. Let's look at this scientific claim. ACE2 receptors are involved in coronavirus infection. We want to understand if this fact or this claim is right or wrong. How do we do that? We like to find some important piece of information among a large collection of scientific data together with scientific knowledge bases. For example, find a sentence like this, that patients treated with this particular drug experience a reduction in symptoms, right? And understand that, okay, this sentence probably leads to the point that this scientific claim is correct. So I'm gonna delve into a bit deeper for this particular example later throughout the talk. But this is kind of the main idea. How can we use extrinsic applications to evaluate textual comprehension and reasoning? And this is our goal in my lab at UW. We are focusing on this problem across different areas in artificial intelligence, mainly focusing on natural language processing, also a little on computer vision, because we are looking at multimodal data. And our main goal is to be able to develop algorithms that are interpretable, are able to explain their decisions to humans, are robust, they can be generalized across different domains, and scalable, meaning that we can potentially use them on the, low resource devices like cell phones and so on. Okay. So most of this talk will be about our work on question answering. Let me define it a little bit more closely. Basically, the idea is a question comes in, and it has people have used many different names for it, like question answering, reading comprehension, machine comprehension, and so on. But the main idea is this: a question comes in, which is usually a well-formed input. Then a system will sit in the middle and it outputs a response, right? Which is usually a well-formed in these days NLP research. But the main idea is that when we have a question like this, who sang More Than a Feeling by Boston, the question will be cross-referenced across a context, which can be sometimes a paragraph, sometimes can be a structured data like Freebase, or unstructured larger scale data like Wikipedia, right? And then the goal is to find the answer within this context. So this is kind of the big picture definition of question answering when I refer to question answering here. Open question answering, again, I'm just defining some phrases here, is developing a system that can answer any factoid question that is usually independently written by humans, right? Who sung More Than a Feeling by Boston. And when we deal with textual question answering, like open question answering, we think that the context is Wikipedia, okay? Which is usually really large scales. It has more than 5 million articles, but the goal is to find the answer within Wikipedia articles. Okay. This is really hard. Why? Because we are talking about 5+ million articles. How do how do researchers usually try to address this problem? Is build a pipeline in which they first retrieve a few articles or paragraphs that are potentially related to the question, and then do reading, which is to answer the question within those few articles or paragraphs. How do they do retrieval? This research has started many years ago. Like the simplest approach is to do word level retrieval, for example, using TF-IDF features. This is computationally really cheap, relatively good because it allows us to extract web pages or documents that are potentially related to the question. And very recently, people have made a lot of progress in this domain in NLP, which is, for example, they use dense passage retrievals. That's kind of out of the focus of my talk here. And then once these few articles are retrieved, then new algorithms will come in and then read and comprehend these articles. And the state of the art in the NLP research these days is that the input will come in, people or algorithms try to encode questions and the paragraphs using one of these Sesame Street characters that have become really famous in NLP literature, which are like a very black box definition is they are deep neural models that try to encode text using kind of language model objectives and so on. And then on top of that, a task-specific layer will come in and tries to extract spans within those articles or paragraphs, okay? And usually this has been trained end-to-end, meaning that larger scale data sets are being created for kind of answering these questions, where the question comes in, the answer would like to be, we would like to extract the answer. Okay, So I just try to give you a little bit of background about the status of question answering and open question answering in NLP. And in this talk, I would like to talk about some of our recent efforts on open question answering, where we look at different forms of question by introducing new challenges or developing novel algorithms that look at more complex questions and then try to answer them. Okay, so this is the first work I like to talk about, which is multi-hop question answering, led by my amazing student, Akaria Sai, which she's just finishing her first year. And this work is published at ICLR last year. Okay, let's look at this question. When was the football club founded in which Walter Davis played at center forward? Okay, so this is again a question for Wikipedia, but it is different from the earlier question in which I showed you, because in order to find the date that this football club is founded, we need to first find out what is that football club, right? And the only information that we have is the player name, right? So the football club is not given to us. So if we use this kind of a standard pipeline of retrieving and then reading, potentially just doing regular retrieval won't help us to find out what is that football club. Like most likely the date of founding that football club would be inside that football club article. But we have a clue here, right? That is the player name, right? So this is why it is called multi-hop questions, because you need to do a few steps to find the final answer. So what is the clue? We first would like to go and find the football club that this player played, right? Which is this football club here, Millwall, right? Because potentially it is easy to retrieve the article related to this player. And then from that, we would go to the Wikipedia article of that Millwall football club and then find out that this is founded in 1885. But directly retrieving this paragraph is hard using kind of a standard retrieval or kind of a state-of-the-art retrieval algorithms up to that. There are different approaches to that, which is try to decompose the question to simpler questions, right? For example, we first form this question one, which is what is the club in which this player has played? Then retrieve that team or kind of answer this question, find out what is the answer, and then in the next question, understand when is that team founded. Okay, so this is kind of a direct way of answering this question, which is try to decompose the question into its components, like into simpler form. And this was our approach a year ago. But then in this paper, we thought, okay, what if we kind of try to directly answer that question by including structured data, in particular Wikipedia graph, to guide the retrieval for us, and then build algorithms that allows us to learn to retrieve these reasoning paths, and then kind of build this retrieval reading framework that I was talking about. And then we show that it gets really good results across different OpenQA datasets. Okay, let's see how we do that. We basically first try to construct the Wikipedia graph. This is basically very simple. Every node in the graph are Wikipedia articles, and the nodes are connected to each other according to the hyperlinks that exist in Wikipedia. Then we sequentially retrieve pages by finding the reasoning path. So for example, this is like a snapshot of the Wikipedia graph that we are dealing with here. And then when we want to find out the reasoning path, we first retrieve the player, and then from the player, we're going to retrieve the team. Then like kind of like the main algorithm that I described earlier, our approach is also a similar pipeline, but instead of retrieving a few articles, we would like to retrieve reasoning paths, right? And then these are different reasoning paths that are extracted or retrieved. And then we look at the top K reasoning path, try to see what is the answer given each reasoning path, and then try to rank them. Just a little bit more details about how it works. We use recurrent neural networks to sequentially retrieve these reasoning paths. So for example, this is our Wikipedia graph. We initialize the search using the word similarities and TF-IDF search. Then we build this sequential reasoning step, which is at each step, we would like to decide if we want to add the next article or not, right? According to the links that we are seeing in our graph. And then we continue the search until the end of evidence token is retrieved, right? This is kind of how the whole reasoning path is being retrieved. We use beam search to find the top K reasoning paths. And then once each of these reasoning paths are retrieved, let's say now we have two reasoning paths. One says ABD, the other says GNH. Then we run our reader algorithm, which we just used simple Sesame Street type reading algorithms to use those paths to find the final answer in the end, in the last paragraph. For example, the answer according to the last paragraph here is something, the answer according to last paragraph here is something else, and then we try to rank these reasoning paths, okay? So I won't go into the details here, but in order to rank reasoning paths, we kind of try to use the final answer as our guide to see what is the most likely path here. Okay. So we trained the networks over there and then evaluated over 3 different NLP data sets, in particular AmbigQA, Squad Open, and Natural Questions Open. And we saw substantial gains in each of these data sets. So probably you would have expected same thing, that our results are good. That's why I showed the method. But in order to understand that what components actually helped us, we observed that we really get large performance gains from our sequential retrieval step rather than kind of batch retrieval that previous approaches were doing. We also noticed that instead of just relying on the top reasoning path, looking at different reasoning paths, and then kind of try to look at this interplay between retrieval and reading helps us to find what is the best answer. And we also use different ideas for how to train the retrieval algorithm or the reader algorithm by doing hard negative mining that were designed to show that what reasoning paths are worse, what reasoning paths are better. So for the details, please refer to the paper, but like all of those components actually helped us. Okay, so this is kind of almost the end of the first part of the first project that I wanted to talk about. Just to summarize, here we looked at questions that required complex reasoning, and we leveraged the structure from Wikipedia graph to guide our search to help us to better retrieve these reasoning paths. So this works really great, work on factoid questions on general domain. It is kind of interpretable. Why? Because we are able to explain our decision based on the nodes and the pages that are being retrieved from this Wikipedia graph. So the next questions that we would like to answer are these. How does this work on other domains? Also, in this case, similar to many other previous work, we assume that there is only one answer to the question that are being asked. What if the questions are ambiguous and we are not sure like what answer the user is interested in? This is a new recent work that is going to be presented at EMNLP 2020 and led by my amazing student, Savon Me. Let's look at these two questions. What season does Meredith and Drake get married in Grey's Anatomy? Or who was England's prime minister during World War I? None of these questions look ambiguous if we just look at these questions. But when we bring the context in, which means that we bring in the corresponding Wikipedia pages, we know that there are potentially multiple answers. For example, in season 5, these two people unofficially get married, but then they officially got married in season 7, right? We don't know what is the main answer that the user was asking, like was interested in. Or in terms of the prime minister, there were basically two prime ministers, one serving from 1908 to 1916 and the other from 1916 to 1922. We are not sure, like basically the user by himself doesn't know that the questions are ambiguous. And we noticed that over 50% of questions from natural questions dataset that are collected from humans or actual search queries are ambiguous. And this is basically inherent in open question answering because users are trying to seek for information, therefore, and they basically don't know what responses they are looking for. Okay. How can we provide answers to such questions? Would it be fine to say there are multiple answers, season 5, season 7? This is probably less helpful, right? Because like the user won't understand why the system would give them two responses. If we write down textual descriptions like this happened, they got unofficially married in season 5, officially in season 7, again, it is less clear. It is a non-trivial evaluation for if the system has provided good answers or not. Our proposal is this. What if we explain the context in terms of forming new unambiguous questions that minimally changes from the original questions? Like, for example, we added the word informally here and legally here, where now the answers are unique, are completely clear, right? Or here it would be in the beginning of World War I, here will be in the end of World War I. And then the questions will become clear. So this is basically the challenge that we introduced where we define explicit answers corresponding to questions that are changed just a little bit from the original question, but now they have unique answers. We introduced this new task of ambiguous question answering. We created a data set by annotating an already available questions from an already available open questions by kind of disambiguating them, and we develop a few baselines to answer these questions. Okay. So just to reiterate, we basically, through this work, we embrace ambiguity that are inherent in open domain question answering, because many of those questions are unintentional and they are subtle. We form the task this way. Given a prompt question, we would like to find out what are the modification of the question and the corresponding answers. Where either of these answers are equally plausible, but these questions are minimal modifications of the original question. So for data collection, this is pretty challenging, right? Because it is hard to ask human annotators to come up with all possible unambiguous questions that exist given an ambiguous question. We try to solve that issue this way, where two independent generators start to disambiguating the questions. Like, for example, the first generator says, okay, this is fine, the question is not ambiguous. The second generator would come and disambiguate the question. In order to fix these issues, we brought a validator who tried to kind of see if these questions are correct or not. In particular, we received relatively lower agreement in the early phase, but really high agreement later. Basically, we say the collected questions are pretty accurate, like we have 89 F1 agreement, but probably we are still missing recall, right? There are other forms of disambiguations that our current data set misses. Some statistics about the data, it includes 14K questions. These are different types of disambiguations that the users did, like event references, different properties, time dependencies, answer types, and so on. Please refer to the paper for more details. And then let's talk about different baseline algorithms that we created. One important requirement for solving this task is to add the capability of finding multiple answers when we answer a question. Most of the current systems just try to answer one question, or like find one answer for one question. What we did was a very simple baseline, which is, okay, use one of the already available machine learning algorithms to do question answering, and then just put a threshold over the likelihood, right? Say we're gonna look at the top K answers. And in the second approach, we try to generate a sequence of answers, and then we put separators in between. For question disambiguation, this is what we did. We basically get the prompt question, we pass it to a sequence-to-sequence model, and then we look at we generate an edited question. Okay. We also try to use a modified democratic code training algorithm where its main idea is this. We have a really large scale data set called natural question open, which includes open questions. But they are only annotated with a single known answer, right? So we thought this is but we know ambiguity is inherent in that data. So we like to use that as weak supervision to help us generate multiple answers. This is how we did that. We used it. We basically used our algorithm that generates multiple answers, trained on our kind of a smaller scale data. And then we run it over the natural question data. But then when we did that, we start at inference time, we start with season 5 when we knew like that is the correct answer annotated in natural questions. And then we put separators at the end, let the model generate more answers, right? Sometimes it stops and sometimes it adds more answers. And we basically tried C instances, like multiple instances of our model to be kind of answering questions this way. And then if multiple of these systems answer multiple answers for this question, then we add those answers to the data, and then we iterate multiple iterations here. And then using this, we actually see some gains. Okay. So this is the first baseline we tried, which is just look at the question, try to see if the model can disambiguate and answer questions. See the performance is pretty low. Then we tried the DPR plus thresholding, the first baseline. We saw some improvements. Our sequence generation model improved a little bit over the baseline, but really not as much as we expected. But then when we use the weak supervision and then the code training approach, we saw most gain. So still the performance is very low. So across different metrics that we've introduced for the task. So this means that there is still a lot of room for improvements, and we invite the community to actually work on this important problem. And we are still seeing some people kind of operating in this domain as their most recent system even improved over our code training approach. Okay, and here is the link to the data. Okay, so I know I'm not supposed to stop for question. For that reason, I'm gonna move on to the next topic, which is both the approaches and both data sets that I was talking about were mostly looking at questions about general domain. What happens if we look at new domains that it's harder to collect data, like scientific claims? This is also a very recent work. It's going to be presented at EMNLP 2020, led by my amazing students, Dave Wadden, and also in collaboration with a semantic scholar at AIT. Okay, so this is the task that we are interested in, which is given a scientific claim, ACE2 receptors are involved in coronavirus infection. We want to see if we can support or refute this claim. So when we searched over a research corpus, and if we find this sentence, patients treated with this drug experienced a reduction, P is smaller than 0.01, in symptoms. This sentence would actually provide some rationale for this scientific claim, saying that this is supported. But it's actually really still hard to understand why such sentence supports this scientific claim, right? So an added benefit of or challenge of claim verification in scientific domains is that we really require to do multi-hop reasoning and complex reasoning and aggregate information across different sources. Let's see why. So first, we need to consult scientific background knowledge to know that this drug actually disrupts ACE2 function. The second thing is kind of having some knowledge about statistical and kind of understanding, showing that when we say P is smaller than 0.01, this is actually statistically significant. The third point says patients experienced a reduction in these symptoms. What patients? Really here, we need to do some natural language processing analysis, go a little bit earlier in the article, show that, okay, learn that these patients have COVID-19 symptoms. Okay, so, okay, these patients have COVID-19 symptoms. And then a causal effect, meaning that disrupting ACE2, reducing symptoms, means that ACE2 is involved in infection. So we need to take these 4 steps to finally understand that this rationale is actually supporting this scientific claim. So basically, this is a very important challenge because we are talking about these emergent domains like COVID-19, which is really hard to collect data. And these are important domains to be able to help scientists and also lay people to explain these claims to them. Okay, so how do we tackle scientific fact-checking? We construct a sci-fact data set, we define the task and develop baseline models, and then we verify some real-world claims. So I've mentioned multiple times, data collection is very challenging. It's not that we can go to crowd workers and ask them to write down claims. It's even challenging to ask experts, like for example, medical students or medical experts, to come up with different claims and write down different claims for us. Like, so this is quite expensive evidence. But the key observations that we had was when one paper cites the other paper, they are basically like in the, for example, related work section, they probably try to summarize claims that are mentioned in the second paper, and then they try to kind of find the evidence in the corresponding paper. So this is how we start collecting data. We look at the citing paper, we look at the sentences in related works. They are still a bit complex, so we ask some experts, in particular medical students, undergraduate students, or biology undergraduate students, to simplify these sentences such that now they are talking about atomic claims. And then we look at the cited papers and try to see, and then ask another group of annotators to read those paragraphs and see if these papers support or refute those claims. In comparison with other fact-checking data sets that exist in the NLP community, like Fever is about Wikipedia facts, Snopes is about political news, our facts are much smaller. Still, it's much more challenging compared to, for example, collecting Fever, like a Wikipedia or political news facts. But we call our facts or our claims natural because they are extracted from scientific papers. Similarly, this Snopes is extracted from news articles, but Fever is kind of synthetic. People try to, like crowd workers, try to modify sentences in Wikipedia. Therefore, like the scale is much larger. So we are defining this task given our data set, given a scientific claim. We would like to build a claim verification system that looks at different abstracts in a scientific corpus, find relevant sentences to the claim to see if it supports or refutes the claim. And notice that we can have abstracts that actually support this claim. We can have abstracts that would refute this claim. And I mean, as you can see in scientific literature, especially about COVID-19, that the claims are being supported or refuted throughout different papers. Modeling pipeline, we did a very simple approach similar to the basic algorithm that I described for open question answering, which is given a claim, we want to retrieve abstracts that are related to that scientific claim. Then we would like to find out what are sentences that are either support or refute the claim using a rationale selection algorithm, again, relying on Sesame Street algorithm, like language models. And then given the selected sentences, we want to predict the labels, which is if this claim is supported or refuted. Okay, so I won't go into the detail. This is just the high-level idea. We showed that our data set is useful. Like the full pipeline result is still pretty low, like about 46%, which shows that even though the data set is small, it is useful to like compared to just using, for example, other claim verification data sets. But still, there is a huge gap for the scientific or NLP community to work on this data. Here we did a few ablations. If we know what abstracts we are talking about, like we remove the abstract retrieval step, we see a huge gain, which is like almost 72%, which means that it is important to find relevant abstract or retrieve relevant abstract to the process. Also, if we use gold rationales, meaning that what sentences are potentially related to these claims, now our numbers are much higher, almost 83% accurate, we can say, if this sentence supports or refutes the claim. And we still see some progress in the community. Okay, so we have a really nice demo. I wanted to show the demo, but I thought it is hard over Zoom. Instead, I show a few snapshots of the demo. So here is how you can kind of enter your claims. We have some sample claims. In particular, we asked a medical student to write about 40 COVID-related claims, and then we verified them using our system. We noticed that we could reliably answer more than 60% of claims correctly. Let's look at some example. SARS-CoV-2 binds ACE2 receptors to gain entry into cells. When we search it over our data, we found this article that supports this claim. We also have this button or this kind of interaction with our users to see if this is relevant to the claim or not, and is it actually supporting or not, to collect more data this way. This is actually a correct sentence that supports this claim. We also had another claim, like COVID-19 is a biological weapon. We found this article, which is a preliminary assessment of novel coronavirus knowledge and perceptions in Nigeria, that 99% support this claim. And this is actually correct, right? This article says it is supporting this claim, but this is wrong, right? So this is another kind of the future work that we like to work on, which is source credibility. Now we are just saying there is a claim, can be verified given this article or not. But right now we don't have a way to see if we can, this source is credible or not. And that's kind of this user feedback would be very helpful for us. Okay. Another thing I mentioned, you remember when we wanna answer these type of claims, being able to reason and then this kind of multi-hop reasoning is really important. So we also invite the research community to work on this multi-hop reasoning, bringing in external knowledge, and so we can answer these claims more effectively. Okay, so I think I have a few more minutes, so I would like to also announce another work that we have it's going to be on arXiv today, actually, on extending open question answering to multilingual domains. And again, this is a work led by my amazing students, Akari, and with some collaborators at Google. So multilingual OpenQA is really important task. In this work, we introduce a cross-lingual answer retrieval task. We construct a larger scale multilingual QA data set, and we developed a few baselines for it. So I'm not gonna go into details here. I just wanna give the intuitions, which is knowledge resources in non-English, for example, Wikipedia or other sorts of non-English resources. It's kind of 40% of them are non-English. But most of the research in NLP, and especially in question answering, are mostly limited to English. Again, mainly because of the data sets that are being created using English crowd workers, like English domains and so on. So it's much easier to collect data using English. People started looking at multilingual question answering, but most of the previous work used translation-based, how they basically take one of the data sets that exist in English domain and then try to translate those questions into other languages. But unfortunately, the data sets have become biased toward English culture. Like, for example, there are too many Super Bowl related examples in a Japanese language, right? Probably a Japanese user won't be interested in questions about Super Bowl in the US. There is the most recent data set, which is called tie-dye QA, that uses non-English native speakers in different languages and tries to collect answer within those languages, with those speakers, which is awesome. But they have one assumption, which is the answer to their question can be retrieved in the Wikipedia of that particular language. But we know this issue exists, which is information scarcity. A lot of languages don't have enough resources. For example, in low research languages, like for example, Bengali, 60% of Bengali questions are unanswerable because they couldn't find the answer in the Wikipedia of Bengali. Like questions like this, who is the founder of Detroit Institute of Art? Like there is no Wikipedia article in Bengali about that. Another important problem is information asymmetry, which is the questions are in their own culture. Like, for example, there is a Japanese question, like, where did this person learn silk reeling technique? Like, we couldn't find this answer in English Wikipedia, that it exists in Japanese Wikipedia. But on the other hand, there are some questions like, what did Ron Paul major in his undergrad? There is a Japanese article about Ron Powell, but it is much more simplified compared to its corresponding English Wikipedia. So it is important to be able to also search in other languages to find the answers within those Wikipedia articles. So we introduced XOR-QA, which involves cross-lingual document retrieval. Basically, we have questions in kind of multiple languages, and the answer to the question can be retrieved either in the target language or in English. Basically, we used it as a pivot language, and we are planning to extend it to other languages as well. And this way, now we are able to define new tasks, which is XOR retrieve, XOR English span, and XOR full, where in XOR retrieve, the goal is to find only retrieve documents that are able to answer the question, or you can find the answer to the question in those documents, which can be in the English Wikipedia or in the target language. XOR English span, where, because the evaluation would be simpler, the idea is, given a question, we would like to find the answer in the English Wikipedia. Probably we have a lot more unanswerable questions this way, but still, can we just find the corresponding phrase in the English Wikipedia? And then the full setup, which is given a question in a language, can we find the answer in the target language? So the data would be released basically next week. And again, I wanted to advertise this work and encourage the community to work on this. Okay, so I think I still have a few minutes. So I would very quickly go over the last portion of my talk, which is unified question answering. So I have mentioned this several times, that there are many different question answering data sets being created across natural language processing. And the way that people create them, they use many different formats. Like we have multiple choice question answering, we have yes, no, we have extractive, abstractive, open domain. Like you've noticed I talked about open domain here mostly. And this is just a snapshot of a few data sets that exist in this domain. But they are all different from each other because the different types of context they have, because of the different formats they have, or unexplored reasoning challenges, right? The machine comprehension algorithms, the question comes in, and then a task-specific layer will come out, and it's gonna be data set specific, right? And because we are just looking at a specific data set, it's actually kind of distance us from broad unified question answering. Here we introduce unified QA with a very simple observation. There is overlap between underlying reasoning abilities that are being introduced in each of these data sets and formats, right? So how can we actually build a single QA system that works across all these different QA formats, and like how can we kind of mix and match these data sets or the reasoning abilities that exist across all these data sets? And our solution is multitask learning. I will just finish with this slide, which is the choice of task is important. People have looked at multitask learning in the T5 paper in particular to show that by combining different NLP tasks, you can get combine all of them, and then you can get good results. But what they conclude is that still that model is not better than a single model for those specific tasks, and mainly because they try to combine too broad of tasks. Here, we are kind of arguing it is important to narrow the scope of these tasks to the boundaries of QA, okay? And the format is pretty simple. We trained a sequence-to-sequence model to answer questions. So these are the choice of the data sets. I'm kind of going fast. But this is the important result, that now we are able to achieve a state-of-the-art result. Like, for example, just using T5, we are getting these numbers. But when we use our unified QA model and then fine-tune it on some specific data set, we are getting a lot more improvements, because they, like, all these data sets talk to each other, and then we can kind of use reasoning abilities in one data set to generalize across domains. One other kind of quick things I want to show is it also is really helpful in zero-shot learning, where this is kind of a very recent paper, and we are still trying to understand their evaluations. But this is a paper from some other groups that they do zero-shot learning on different types of STEM types, multiple choice questions, social science, multiple choice question, and then compared to GPT-3 large, unified QA gets kind of similar numbers, whereas our model is much smaller. We are even better than GPT-3. So just to wrap up, I mainly talked about some of recent work in open question answering from my group, and then I ended with building a unified question answering model. And basically, this is the main goal of the research in my group, which is how can we go beyond pattern matching so we can have rich understanding of textual data, be able to do complex reasoning and comprehensive retrieval. And one thing that we are thinking is maybe we should integrate symbolic and neural models to combine these approaches. And thank you.